over the years, I've steered clear of steel wear. And that's simply because it is very difficult to understand. There's a hell of a lot going on, and we don't. I mean, at least looking at the literature, we don't begin to understand all of those things that go on when it comes to wear. As far as the literature is concerned, Bond, because he did just about everything in his day, he's done a lot of work, at least published work. I'm talking about published work now. I think you'll find a number of the ball mill manufacturers have done a lot of their own internal work. Some of it is published, some of it is obviously in-house. Clearly, whatever work they do may well have a competitive advantage, so one can understand why maybe some of that work is not made public. So I can only really talk about what I've learned and what I see in the published literature. So Bond has an abrasion index. Peter Ranichevsky, there's a lot of work done by Peter. Peter worked with me initially. He was on sabbatical. I was running the research program. That was the same time where we developed the drop weight tester. And during his sabbatical, I asked Peter to start to look at wear and could he come up with something. And he started to do some really good work. And he tried to split wear into wear which was caused by corrosion, wear which was caused by abrasion, and wear caused by impact. And he developed a number of different machines, and we started to test them. Peter then finished his sabbatical and went back to his university. He did a bit more work. He then changed universities, did a bit more work. He then left to go to Mezzo, and I think that research work may have stopped. I'm not certain. It never, unfortunately, reached a point where it completed it. We could say, yes, we understand wear. And from a design viewpoint, if you were a designer and you were asked, well, you've got to work out how much steel this mill is going to consume, it never got to a point where you could use it to say, yes, I'm confident with my predictions. I'm surprised over the years our industry has not funded more money on this, because steel ball costs, if you look at them, can easily match energy costs in a grinding circuit. And with the huge thrust there is at the moment about saving energy, yet no attention seems to be paid, or little attention is paid, on the amount of energy that actually goes into making steel balls and liners. There's a massive amount of energy that goes into that. We don't seem to, as a mining industry, to pay that much attention to it. I'm absolutely amazed, but we don't. And I think it's about time maybe the industry did something about it, because we don't know enough about it. So, Bond's abrasion tester. Here it is. This is a brand new one. It has two counter-rotating components. There's an outer drum that goes in one direction, and this slotted basket, call it that, gets bolted onto the inside. And then in the center here, which goes at a different speed, is a spindle which holds two of these blades. One blade goes in there and the other blade goes in there. So the outer drum goes in one direction, the inner one goes in the other direction. And you spin this device up together with 400 grams of rock of that size. And you do that for 15 minutes. You then take everything out. You put a fresh 400 grams of that size, and you do it for another 15 minutes, and you do that 4 times altogether. So you run the whole thing for an hour, and you weigh these paddles, they call them, which Bond specifically said had to be of a particular material type, and the weight loss, the grams lost in that 1 hour, becomes the abrasion index. And now you can read this all up in Bond's paper, but if somebody says to you, have you done an abrasion AI, a Bond AI, that's what it is. What can we do with those equations? Well, Bond not only did he develop that test, but if you read his 1963 paper, he put together, among other things, for wet ball mills, the kilograms of steel lost by balls per kilowatt hour, because they are the accepted units of steel wear, and he gave that formula there, and you can see AI and nothing else is in there. That's his one for liners, and this is, don't forget, wet ball mills, and this is the one for crushers. He also did it excuse me, for rod mills, and he said he collected data and he calibrated these abrasion models to these data. As I said earlier, SAG Mills were really not there in any great extent, so he has no wear model for SAG Mills. How accurate are these equations then? Well, Moly-Cop wrote a really, really good paper. They published it, Procemin, in 2013, and they were studying steel ball wear. And they very graciously, because it's most unusual, published all their data. And these blue points are the data that they published. So this is the measured kilowatt hours per, kilograms of steel that they were consuming per kilowatt hour. And this is what that bond equation actually predicts. Now, all these mills, according to their paper, because these are all different mills, are from Peruvian operations. So they are in this part of the world. The triangles come from another paper, which I'm going to talk about as well, that Newmont Mining published as well. So the bond equation, as you can see, is that dotted line. Don't forget, what we're looking for are our data points to be lined up along that line. You can see at the top there the R-squared value of 0.28, not good at all. So if you're a designer out there and you need to use bond in a project, well, beware, because I think you'll get very much the wrong answer. Now, Moly-Cop, and these are the authors of that paper at Procemin, published their data, and they also put together quite a neat equation for predicting steel wear due to balls. And this is a cut and paste from their paper. I've simplified it, you'll see in my next slide, but I just want to show you how they looked at steel wear. There was this omega E parameter, and omega E is this function. D here is the ball size that you charge with, and this K parameter has this equation associated with it. Now, remember what I said, that the steel wear traditionally is reported in kilograms per kilowatt hour. Now, that's kilowatt hour of the mill. Moly-Cop look at it slightly differently. They represent steel wear as kilowatt hour due to the ball proportion inside a ball mill. And they have their own ball mill power model, and they look at the proportion of the total power that's associated with balls and, I presume, slurry and so on. The Morrell power model inherently does the same thing, and if you want to dig into the model, you can get exactly the same number. But they didn't, in their paper, publish what that power due to balls versus total power is. So I back calculated it from their data, and on average, there's a factor of about 0.79. Now, the only reason I'm saying this is that if you take their paper and you take these equations and you put them in your spreadsheet, which I did, and you do the predictions and you compare those predictions to the actual, you have to remember that you need that factor to align it. It's not a big thing, but you need to be aware of it. What I decided to do was basically incorporate all of that. I took these same equations, but just represented them in a slightly different way. They have exactly the same function, and this is what their equation reduces to, but this time, this is now in terms of kilograms per kilowatt hour of the mill. So it now aligns with what most of the rest of us look at steel wearing, and that's their equation there. And from their work, they said they found that the abrasion index was obviously still important. They had F80 as a term in their equation, and they considered pH, the acidity. So they were obviously looking at slurry corrosion. So let's go back with their data. That's what Bond would give to their data, and that's what their model gives. So you can see huge improvement, huge improvement. And now we have an R squared of 0.76, and you can see it's absolutely bang on that line. So certainly much, much, much better than Bond. So very good model indeed. I do have a couple of problems with it. I did a statistical analysis of their data set, and I could not find that pH was statistically significant. So the stats said that pH, acidity, wasn't in it. The other problem I have with it is that, so let me quickly go back. That is the ball size, and it's to the power of -1. What that assumption is that ball wear is directly proportional to the surface area of the ball. Don't have a problem with that at all, but it says that as the ball wears, that continues. As the ball gets finer and finer and finer, and that assumption assumes that the hardness is the same throughout the whole ball, and we'll talk about that in a minute, and it also assumes that the environment that the balls find themselves is the same, regardless of whether it's big or small. It's not a bad assumption. The thing is, if you look at their data, there's something called cross-correlation, and cross-correlation gives you problems. Cross-correlation because their mills vary from coarse feed to fine feed mills. And if you're a ball mill operator, if you have a coarse feed, you have a big ball. If you have a fine feed, you have a small ball. So F80 and ball size is correlated. And with cross-correlation, you basically find that the parameters are not independent. And so you've got to be very careful when you start looking at significance when you have cross-correlation, because it could simply be the reason that the F80 is there in the first place is because there's an already existing interaction with ball size. You've forced, in their case, ball wear to be proportional to ball diameter exactly. And so I have a feeling that that cross-correlation has caused one or two minor problems. pH is not statistically significant. That does not mean that I don't think that pH is important. It has to be, surely. The environment that you find yourself in, or the balls find themselves in, has to be influenced by the nature of the slurry. It doesn't make sense if they're not. We know enough about corrosion to know that that is an influencer. All I'm saying here is that their data don't quite support that the relationship as what it says it is. I just simply decided, let's do a really, really simple model, and statistically that's what I came up with, which is simply the wear is a function of the diameter to the power of -0.72 and the abrasion index, and I ended up with a model which had almost exactly the same accuracy as the Moly-Cop model. So I'm just toggling between the two. That's the SMC model, that's the Moly-Cop model. So I'm not saying that that model is any better than the Moly-Cop one. It's just a simpler one. It certainly doesn't give you anything better than the Moly-Cop model. It's just something else you might want to consider. When you put the Newmont data in, it was fine for all of the data apart from that one data point, and I have no idea what's going on there, but it's just something, a bit of a warning that we still don't know enough about steel wear, and there are some cases out there where those simple models really don't work at all. So just to finish off with ball mills, why that scatter? Well, there's a couple of things there. One of the things is that the abrasion index test is not a good one from a precision viewpoint. These two guys, Angove and Dunn, did some round robins with the abrasion test, and the coefficient of variation was really quite high. And that's because there is not a uniformity in those abrasion index testers. There's some different models out there, and I think that's giving rise to some scatter in the data. The other thing is, I'm certain one has to have in either of those models some effect due to what the ball's made of. Some of you may well have been working in situations where you've gone to, say, very high chrome steel balls because you want to reduce the wear. Sometimes you'll find it's worked, sometimes not. But certainly in certain cases, you change the composition of the steel and it definitely has an effect on the steel wear. There's nothing in either of those models that accommodates that at all. The heat treatment, the through hardness, all of those factors surely must influence whether it's cast or whether it's forged. So all those other material aspects have some influence, and those models simply don't incorporate that information. Here's what I mean about hardness profiles. This is from a published paper, and it shows this is the distance through the ball, what the hardness does. One of the balls, you can see the hardness falls right down as you go towards the center of the ball. In this case, it doesn't. It's fairly static. One would expect that the wear rate of these balls would vary as the balls wore away and got smaller and smaller and smaller and smaller. Expectation would be that. Here is some hardness profiles, forged versus cast. These two straight lines here are for some cast balls. This one here is from forged balls. Once again, surely one would expect different wear rates depending on these two balls. And here is a graph showing just that from this one author, where he looked at the cumulative mass loss on a lab machine, and one of these is for forged balls and one of these is for cast balls. So lots of stuff that we still don't know about that should be in there. What about Grate versus Overflow? Is there a difference in ball wear there? Bond said no. He said he couldn't find any difference, which is interesting because personally, I would have expected a difference. And when I found this paper by these two guys, Dana and Van der Bosch, they worked for Magato. And I know that Magato have done a lot of pilot test work, and over the years I've worked with them in Belgium as well as in South Africa, not necessarily on wear, but they've had a number of pilot plants. And they said very clearly that according to their data, that there's 30% less grinding media wear in an overflow compared to a Grate discharge. Now, it's got nothing to do with the Grate. This comes back to slurry pool versus no slurry pool. In a Grate discharge mill where there's no slurry pool, my intuitive feel is that there's more chance of two steel balls contacting one another without a slurry being in between and somehow cushioning those two balls. Whether that's a good picture or not, I don't know, but intuitively my feeling is surely there must be something like that going on that maybe explains why steel wear, at least according to Magato, is less in an overflow mill. All right, to quickly finish off, future for ball mill wear. Great as a researcher. I know I'm retired now, but if I was in the field, it'd be great to get some more data, and probably there is data out there. And as I said before, you really do have to consider other factors than just simply the abrasion index. It's not good enough if you want to do the job better. Right, SAG Mills. No, there's nothing there. There's nothing generally accepted for steel wear in SAG Mills. Aidan Giblett and Jim Seidel in 2011 published this paper, and they came up for SAG Mills with this really interesting correlation to say the wear was a function of the JK drop weight test AB values. Really interesting. And they also said that the steel fraction, that's the ratio of the steel to ore in the mill, had a significant impact on the steel wear of Newmont's SAG Mill operations. They tried Bond out, horrible, but then let's be fair, Bond never said it should be any good for SAG Mills. And this is what they came up with. Not bad at all, just on ore hardness. And they made the argument that surely ore hardness in a SAG mill would have some impact on what was abraded away in the mill, whether it was liners or balls. My concern about that model, I said to you before, AB is non-linear. Hate non-linear parameters. So I took their data because it was all published, and I decided to take out the non-linear AB and put in the linear MIA. Comes from an SMC test. And I also decided to use their steel fraction, that's their FS in there, and they didn't have ball diameter. There wasn't a big range in ball diameters in their data. And I just simply looked at it from a simple statistical fitting operation. And these were all statistically significant, and that equation popped out. And it gave a much better fit. The R squared here is 0.93 rather than 0.7. So to finish off, mill liners, I basically can't tell you anything about. I have no data about mill liner wear. I've not seen anybody do anything systematic to do with mill liners. Bond has a mill liner wear equation, and if you look at it, it looks like his equation consistently predicts that liner wear is about 7.5% of ball wear. That's a working figure. Just as an exercise, I thought, well, I wonder whether it's all driven by area. Just as I wonder, because wear generally is accepted to be air related. So I took just a typical ball mill, did some rough calculations of what the liner area is compared to the steel ball area was, and divided one by the other, and I got round about 7.5%. Does that prove anything? No, not at all. That might be the start of somebody's master's thesis to see whether it was rubbish or not. But if you think about it, I mean, there's no doubt that the amount of steel worn away in liners over the life of a reline, for example, in a mill, compared to how much steel balls, it is much, much less. Okay, with that, I will finish. That is the end of the masterclass.